In this video, I want to talk about a third type of proof, a proof by contradiction. And again, let me remind you of when a conditional statement is false. It's exactly when the if part is true and the then part is false. And a proof by contradiction, in some sense, uses that fact right from the get-go. Let me explain what I mean. So here is indeed that dreaded row. And what we're going to do in a proof by contradiction is we're going to assume we're in this situation. Well, let me use a different pen. Here we are. We're going to assume we're in this situation. So assume that P is true and Q is false. That's going to be our idea. And you're thinking, why are we going to do this? Well, the idea is, if we do have a conditional statement that's always true, well, if we assume that the if part is true and the then part is false, something will go wrong. Something will blow up mathematically, because this is always true, so this situation will never happen. So we'll run into some contradiction somewhere. And a common one you'll see is you'll find some property is true and that property is not true. And that's the most likely contradiction that you'll see. But let me kind of show you an example of one so we can see how this works. So we have this problem, show that the sum of a rational and an irrational number is irrational. So maybe pause the video now and try and write this as a conditional sentence, an if-then sentence. See if you can do that. Okay, now that you're back, the way I would write this is, if you have the first number, let's call it x, if x is rational, and your second number, y, if that's irrational, so it's not able to be written as a fraction, so an integer over another non-zero integer, then their sum, x plus y, isn't rational, it's irrational. So that's a good way of thinking about this sentence as a conditional. If your first number is rational and your second number is irrational, then the sum of them is irrational. And it doesn't matter if you wanted to call the first number irrational and the second number rational, it doesn't matter. Addition is commutative, so nothing's going to change. And we'll talk about more formally how to deal with situations like that in a coming video. But for now, let's just do it like this. Okay, so we're going to prove this by contradiction. So let's do a proof, and let's tell people we're doing it by contradiction. So what we're going to do is we're going to assume two things. We're going to assume the if part is true, so we're going to assume x is rational, y is irrational, and we're going to assume the then part is false. So the if part true, the then part false. So we're going to assume that x plus y can indeed be written as a fraction, as a rational number. Okay, so let's go ahead and do that. So the first part is we're going to assume, let me do it in black here. Assume that x is an element of the rationals. So what does that mean? So that means that x can be written as some integers a and b, where it's a over b, where of course a and b are integers, and we don't want a denominator of 0, so let's tell people that b isn't 0. Let's actually break this section off so that we have a little more room to deal with and things are a little more clear. So let's say there. Okay. So we assumed x was rational. Also assume y isn't rational. It cannot be written as a fraction, an integer over another integer. And that's kind of the key here. The contradiction we're going to get, in fact, is that we're assuming y is irrational, but we're going to show that we can write it as an integer over another non-zero integer. And that's going to be your contradiction. So pay attention to this assumption here. So both of those together is assuming that the if part is true, and we're going to assume the then part is false. Also assume that x plus y is rational. The then part is false. So we can write the sum as, say, c over d for some c and d that are integers. And of course, d can't be 0. Okay, so the first part here, this is the if part being true. So this is p true. And here, we're assuming the then part is false. Okay. And we're going to show that something goes wrong, that mathematics blows up. So let's go ahead and do this. So consider x plus y. Well, we know x plus y equals c over d, because we assumed that. That's by assumption. But we also know x equals a over b. So we have a over b plus y equals c over d. But if we solve for y, if we subtract a over b from both sides, let me do this over here, we get that y is c over d minus a over b. Just subtracting a over b from both sides. And then subtracting these fractions, just getting a common denominator and subtracting, we get that y is b times c minus a times d over bd. So, what do we have? Well, we know that the numerator here, b times c minus a times d, that's going to be an integer since it's just the difference and the product of some integers. So we know that bc minus ad, and of course b times d, that's just the product of two integers. So that gives us an integer. So we know those are both integers. And we know that b times d isn't 0, since b and d are both non-zero. Remember, we assumed that. B was non-zero, and d was non-zero. Well, what do we have? We just wrote y, indeed, as a rational number. So we showed that, thus, y is indeed a rational number. But the problem with that is this contradicts this here, which I'll call star, I guess. Let me call this expression here star. So this contradicts star. So we ended up with a contradiction. So, what does that mean? Let me erase. It's getting a little messy, guys. Sorry, I'm running out of room, but that's okay. I'm just going to erase our table up here and continue the argument here. So I'm going to move up here. So this contradicts star. Thus, well, let's think about it. When we assume the if part is true and the then part is false, we were in the dreaded row, we showed that that can only be the case when y is an irrational number and y is a rational number. So there's our contradiction. We have both y is rational and irrational. So that just never happens. Contradictions are never true. Thus, our original conditional statement is always true. And we're done. So again, the logic with this one is, well, we assume the if part is true, the then part is false. We assume there's kind of, you can think of it as a counterexample to this statement. So a rational and irrational number that sum to a rational. And we show that if that does indeed exist, mathematics blows up, where this irrational number, which cannot be written as a fraction, can indeed be written as a fraction, an integer over another non-zero integer. So it's part of the set of rationals, which is not an irrational number. There's our contradiction. We have y is irrational and y is rational at the same time. Impossible to happen. So the only counterexamples are when mathematics blows up. So that means there are no counterexamples. Thus, our statement is always true. Let's look at one more example. This is kind of the classic one. So we want to show that square root 2 is irrational. Now, you could write this as a conditional. So I could write if n is indeed the square root of 2, then n is irrational. That's kind of making this statement into a conditional, no problem. And this totally works. A lot of mathematicians, they won't. They'll just see the statement, show that square root 2 is irrational, and they'll say, all right, I'm going to assume it's false and show that mathematics blows up. So that's kind of the same idea. In some sense, if you want to, the same logic applies here. This isn't a conditional, but it's just some statement. So let's call it P, and it's either true or false. And if you assume it's false, you can show that mathematics blows up. It's the same idea as with conditionals, but if you prefer to write it as a conditional, you can do that. So here we're going to assume that n is the square root of 2 and that n is rational. So let's go ahead and do this. So we're going to assume, or let's say proof first, my mistake. I'm getting ahead of myself here. So proof, and this is by contradiction. Again, when you're doing a contradiction proof or a contrapositive proof, you should tell people that that's what you're doing so it's really easy to see what method you're using. So this is a proof by contradiction. So we're going to assume the if part is true, so assume that n equals the square root of 2 and that n is rational. So we're going to assume the square root of 2 is rational. What does that mean? Thus, we can write the square root of 2 as a over b for some a and b in the integers with b not being equal to 0. And I'm going to add an additional condition here that I wasn't particularly precise about later. But I'm going to pick the a and b in this case so that this fraction is in lowest terms. Furthermore, we choose a and b such that a over b is in the lowest terms. And what does that mean? It means that there's no common factors between a and b. There's nothing we can cancel out. Which means that the greatest common divisor, the greatest common factor of a and b, is 1. There's no non-unit factor. So the GCD, greatest common divisor, of a and b is 1. There's nothing to factor out and cancel to reduce this fraction. That's key. And that is where our contradiction is going to come up. Remember, we're picking a and b so that this fraction is in lowest terms. That's really important. Okay, so let's consider, let me do this in black again. Consider square root 2 equals a over b. All right, what I'm going to do is I'm going to square both sides. If I square both sides, well, what do I get? I get that 2, square root of 2 squared is 2, equals a over b times a over b, which is a squared over b squared. B squared still non-zero. Everything works. Okay. And what do we get here? We get that. Let's multiply both sides by b squared. Maybe I'll write this in. Multiplying both sides by b squared. B squared's non-zero. So we get that 2b squared equals a squared. So what did we do? We wrote a squared as 2 times some other integer. So we know that since b squared is indeed an integer, it's just b times b. We know b is an integer, so b squared is an integer. We've written a squared as 2 times an integer, so a squared is even. We have that a squared is even, and thus, by an example from the previous video, I believe it's 11.1. I'll put a question mark there because I'm not 100% sure, but I'm 99% sure. It might be 11.2 or something like that. But the first example we did in that was if n squared is even, then n is even. We've proved that, so we can use that now. Anything we've proved, we can use. It's a result. So we have, by example 11.1, we have that a must be even. So we can write a as 2 times k for some integer k. Okay? So that's key for us here. A is indeed even. So let's plug this back into the original expression. Or equation, I guess. We have that square root 2 equals our even number a, 2k over b. I'm going to do the same thing. I'm I'm going to square both sides again. There we go. And of course, that simplifies to 2 equals, well, 2k times 2k is 4k squared over b squared. And again, let's get rid of that denominator. I'm going to multiply both sides by b squared. And what do I get here? Let me scroll, give myself a little more room. Don't worry about this page number here. Forget that exists. So I'm going to go here. And we get that 2b squared equals 4k squared. And I'm going to divide both sides by 2. And we get that b squared equals 2k squared. So what does this tell me? Thus, b squared is even, since k squared is an integer. Maybe I'll write that. By the definition of being an even number, even integers are 2 times some other integer. And again, by example 11.1, which we proved, we know that b is even as well. So b equals 2 times some integer. We've already used k. Let's use l for some l that is an integer. Now, if you think about it, we do have a contradiction here. Maybe pause the video, think about how we've shown something that contradicts one of our assumptions. Remember, the GCD of A and B is supposed to be 1. That means there are no common factors. So think about that for a second. Okay, now that we're back, well, we've shown for sure that A is even. That's key. We've shown that B is even. But what does that mean? 2 even numbers definitely have a common factor of 2. So we can say, but since A and B are both even, we know that the greatest common divisor of these 2 numbers, well, it can't be 1. It has to be bigger than 1, since we know 2 is a common factor. That's a greater number than 1, and it's definitely a common factor of A and B, since they're both even. So we know that the greatest common divisor of A and B can't be 1. It has to be larger, because we have at least 2 as a common factor. And there is our contradiction. Let's call this star again. This contradicts star that the GCD of A and B actually equals 1, and thus, well, we run into our contradiction. That means that the original statement must be true. Must be true. So that means that square root 2 cannot be written as a rational number. And a quick review of what we did here, just to make sure that we understand. No, that's not what I wanted to do. Let me scroll, that's better. So, we assumed that square root 2 was rational. So we wrote it as a fraction, as a rational number, integer over another integer. but we picked the integers a and b so that the fraction was in the lowest terms. You couldn't cancel out anything. The greatest common divisor of a and b was 1. We did a little algebra here, some simplification. We found that a squared was even. If a squared is even, a result that we've already proved says that we also know that a is even. So we know a is even. Put that back in, play the same game. So now we put in 2k for a. Do that same thing. We get that b squared is even. We wrote b squared as 2 times an integer. So by that same result we used for a, we know that b is even. But if a is even and b is even, if they're both even, what does that tell us? That tells us that they both have a common factor of 2. So there's no way that the greatest common factor or greatest common divisor is 1. We found something that's bigger. So that contradicts our assumption that these guys are in lowest, or that the fraction was in lowest terms, so these guys have a greatest common divisor of 1. There's our contradiction, so that must mean what we assumed must be wrong. So that means that square root 2 is indeed irrational. And that is proof by contradiction. It's a good method to use for sure, especially when part of your statement has to do with not having a property. Like irrationality is not being rational. And it's kind of hard to write down irrationality itself, but it's really easy to write down rationality. It's a fraction. So when you have expressions that talk about not being something, if it's easier to write down the negation of a property, you should think about using either contradiction or contraposition for your proof. And we'll see examples of all of these types as we continue on in the course.